Assalamu alaikum wa rahmatullahi wa barakatuhu. So today is our lecture 2 and we will continue with the little bit review of what we have looked in the previous lecture. So the first of all we have defined what's an electric machine, and we know that any machine that can convert electrical energy to mechanical energy or mechanical energy to electrical energy. Then we also defined the transformer as the machines because they work on the same principle as the generators and motors of the induction. So although they don't have any moving parts, but still we are using them as a part of the machines. So we also defined the axis of rotation of the shaft, and we said that we can either call that machine rotation as clockwise or counterclockwise. And for this course, we usually take the counterclockwise rotation as positive, while the clockwise rotation as the negative. So then we defined the angular position of the rotor shaft, which will show us that exact position, how much that has been rotated within 360 degree. Then we have the angular velocity, the same as the linear velocity. It's now angular velocity because we have the rotational part, the shaft, and we have different conversion formulas for them. Here we have this Nm is equal to 60 Fm and Fm is equal to megam over 2 pi. Then we define the acceleration, and acceleration is the rate of change of velocity, and we have said that unless we reach a certain fixed speed, there will be a acceleration, because at the constant speed is the velocity is constant, so there will be no acceleration in any object, whether it's a linear or rotational. Then we defined the torque, and we said that the torque is the force that we apply to rotate an object. So it could be a counterclockwise torque if the object is rotating in counterclockwise direction, and if it is a clockwise torque if the object is rotating in the clockwise direction. Then we said that torque can be figured out using this formula. That's the force applied to the multiplied by the perpendicular distance, and we have seen that this perpendicular distance is this one, which is r sine theta. Then we defined the Newton's law of rotation, which says that torque is equal to the moment of inertia times the acceleration, which is similar to the F is equal to ma that we known as the Newton's law of motion. Then we defined the terminology work, and work we said that it is the application of a torque through an angle. So that is how much work is done by applying a torque. Then we defined the power, and we said that the rate of change of work is known as the power, and we know W is equal to tau theta, and then we can define it as power is equal to F omega. So means how much force we are applying, and that's how much its velocity is. So we can find out power in watts by using this relation, and power in horsepower in using this relation if we are given the torque and the rotational speed, which is in rpm. Then we defined these basic principles of the working principles, and we said that the basic working principle is that whenever we have a wire and the current is flowing through it, there will be a magnetic field in the area around it. And we said that if that magnetic field is time changing and we bring another coil or wire close to that magnetic field, the voltage will be induced in that coil, and we call it as the transformer. And again we said that if a current carrying wire in the presence of a magnetic field has a force on it. So if we have the current carrying conductor and we have already produced a magnetic field with another current carrying conductor, so if we bring that current carrying conductor close to that magnetic field, so there will be a force applied on that conductor. So this is actually the basis of motor action. And if we bring the moving wire in the presence of magnetic field, then if we move that wire in the magnetic field, so there will be a voltage induced in it, and this is the basis of the generator action. So this is what we have seen in the previous lecture. Now we will continue here with the production of a magnetic field. So the basic law that governs the production of magnetic field by a current is known as the Amperes law, which is defined as this closed surface integral of the magnetic field intensity. Here H is the magnetic field intensity produced by the net current I net, and dl is the differential. This is dl is the differential element of the length along the path of the integration. So we have to integrate over the closed surface. So I is measured in SI units as amperes, and H is measured in ampere turns per meter. Now let's look at a simple magnetic core of a ferromagnetic material. So essentially all the magnetic field produced by the current will remain inside the core. So the path of integration of Ampere's law is the mean path length. So instead of integrating it over this whole surface, so what we can assume is that we can take this, if you can see here, this is the LC, which is the mean path length. Here it is LC is the mean path length of this core, mean path length of the core. So the current passing within the path of integration I net is then Ni, because n is the number of turns. So if you have only one turn, so that will be just I net will be simply I. But here I net is because of all these means all these wires we have the current that's contributing to the production of this flux. So that's why we will multiply this n times the current that is passing through this coil. So Ampere's law will simply then become HLC is equal to Ni. So we don't need to integrate, because here we have took this as, instead of integration, we have took this mean path length for our and we assume that there is no magnetic field that's been spilled out of this magnetic core. So that's why we will just we will be better for this assumption of taking this mean path length. So here H is the magnitude of the magnetic field intensity, and that's obviously a vector quantity H, and is given by H is equal to Ni by Lc, which is ampere turns per meter. So this is again, once if we see this this picture here, so this is what we are providing giving the current to this coil, and it has the n number of turns. So and the current that current will produce the flux in it. So that flux will be the intensity that will be from the Ampere's law can be calculated from this HLC is equal to Ni. So obviously again this integral is removed just because we have assumed the mean path length of this magnetic core. Now the magnetic field intensity H is the sense of measure of the effort that the current is putting into the establishment of magnetic field, because we are interested in this magnetic field, how much magnetic field we have. So that's why this intensity that H that is we have is that will be defined as the effort that the current is putting in the establishment of magnetic field. So the strength of magnetic field flux produced in the core also depends on the material of the core. So the core material is very important. So most of the time you have seen the hard ferromagnetic material, because ferromagnetic material has the high permeability. So means permeability means that they allow the flux to pass more. If they have the high permeability, low permeability means they will not allow the flux to pass through it easily. So the relationship between the magnetic field intensity H and the resulting magnetic flux density B produced within a material is given by B is equal to mu H. So this is just a linear relation, directly proportional. So the current will be directly proportional to H. That's the net current that will be producing H, and that is directly proportional to the flux density, magnetic flux density. And the constant of proportionality is this mu, and mu is defined as the magnetic permeability of the material. So the permeability of free space, as we know, is known as the mu naught, and its value is well known, 4 pi into 10 to the power minus 7 henries per meter. And mu r, the relative permeability of any other material can be calculated using mu r is equal to mu over mu naught. So that for a given amount of current, 2000 to 6000 times more flux is established in the piece of steel than in the corresponding area of the air. So it means that the ferromagnetic materials are more permeable than the free space. So that's why we use the ferromagnetic materials instead of air. So here we can find out the relation between them, as we know that P is equal to mu H, and H we have already calculated as the Ni by Lc. So mu Ni by Lc. Now the total flux is given by of area is given by this flux, that is the integral over the area of that magnetic flux density times and the differential area. That this is a very generic relationship that we have seen in our junior classes. And so we know this relation well known, that how we can calculate this flux over the surface. So where d is the differential unit of area, obviously, and if the flux density vector is perpendicular to the plane of area, and if the flux density is constant throughout the area, then this equation reduces to. So we have made this assumption that all the flux lines uh, they are perpendicular to the surface. So if they are all perpendicular to the surface A, and if the flux density is constant, and we say that if the flux density is constant throughout this area, then this equation reduces to phi is equal to BA. So obviously we don't need to integrate because everything is constant, so we will just add up, and that way over the area of that flux density. Thus, the total flux then can be calculated as phi is equal to BA, and we know that B is equal to here as mu Ni by Lc by inserting here mu Ni A by Lc, where A is the cross-sectional area of the core. So that's what we have seen here in the previous slides, that area. Now, I hope you have understood this. This is the, I will show you here, this is the cross-sectional area. So that will be, because we are more interested in the flux or the flux density, so we can calculate this flux here, which is equal to BA mu Ni A by Lc. Now let's look at some the solving methodologies of these magnetic circuits. So first of all, we will make some analogies between the electric circuit and magnetic circuit so that we can easily understand them, how we can solve them easily. So in the electric circuit, we have the voltage which is known as the electromotive force, and that is basically used to insert, we can say, the current that can pass through the circuit. So by analogy, we can have the same quantity, we call it as the magnetomotive force or MMF, magnetomotive force or MMF in the magnetic circuits. Now the magnetic circuit will produce that will produce the flux in it, and that magnetomotive force, here we can see that this is beautiful F is equal to Ni, here beautiful F is equal to Ni. So we just use this beautiful F to differentiate it from the force that we have applied to the magnetomotive force. So this is obviously measured in ampere turns. Now this will, the magnetomotive force of the magnetic circuit is equal to the effective current flow applied to the core. So this is equal to this one, and this is the reluctance of the path, And here I is we know that very well known Ohm's law, V is equal to IR. So the current will be I is equal to VR, V over R. So similarly here flux, because this flux is analogous to the current, and this reluctance is analogous to the resistor. So this phi is equal to beautiful F over beautiful R. So again remember, this beautiful R and beautiful F is just to differentiate different quantities that we are using. So I hope you have understood. Once again, if we see that voltage is analogous to this magnetomotive force, here it is electromotive force, current is analogous to the flux, and resistor is analogous to the reactance. Sorry, sorry, not reactance, it is reluctance. So reluctance of the circuit. Now, if we want to find out how the current will be flowing, and that will produce the flux in it, with the direction of that flux can be find out simply using this right hand rule. And if we curl these fingers with the in a direction of like this current flowing here, and if we curl the fingers around this in the direction of this twist of the wires, so the thumb will point the flux that will be produced in this magnetic core. So we sometimes call it the modified right hand rule. And if the fingers of the right hand curl the direction of the current flow in a coil of wire, then the thumb will point in the direction of the positive mmf. So we can find out the positive mmf. Obviously the flux will leave from the positive terminal of this magnetomotive force, and it will flow. So this is how we can find out using this modified right hand rule to figure out the direction of the flux, the direction of the flux that's flowing. And the if you want to make it equivalent circuit, so we can find out how we can put plus and minus to this magnetomotive force. So similarly, the relationship between magnetomotive force and flux is, we know that this magnetomotive force is equal to phi times the reluctance. So reluctance is ampere turns per Weber, and we know that phi is equal to BA, which is this one. And if we just make it some arrangements so that Ni, and we make it separate, and we mu A over LC. So Ni is defined as magnetomotive force, so reluctance will be then defined as mu A over LC. So same series and parallel rules as in resistance are applied to this magnetic circuits, that if they are in series, so they will be added together reluctances, and if they are in parallel, so the flux will be divided in the parallel paths that we know that just like we know that this, if it is two circuits, two resistors are in parallel, so the current will be divided, say I1, and we call it I2, and the sum of their current is I. Similarly, if we have these magnetic circuits, so R1, R2, so the main flux that is flowing here, so that will be phi 1 then, and then it will be phi 2. But if they are in series, they will be just simply added together, just like in the resistance. So some of the approximations in calculations of the flux in a core that we normally use in solving these solving some of the problems. So although that approximations will give us will not give us the exact result, 100% exact results, but most of the time the results are within the plus minus 5% to 10% range of the actual circuit. So for this course, that would be enough for us to understand the calculations based on these approximations. So it will be good enough for using these approximations. So one of the first of the approximation is about the leakage flux. So all we know that whenever there is a flux is produced, that will go into means in the core. So there will be some flux that will be leaked out into the space, and because the space has the less permeability, it will not allow that flux to pass through easily to the other side of the magnetic circuit. So that's why Sometimes we assume that there is there is no leakage flux, and then we can neglect it because it's sometimes very negligible. If we have a very good ferromagnetic materials, then the results will be approximately up to within the plus minus 2% or maybe 3% of the actual values. So, the leakage flux, that says that the magnetic circuit concept assumes that all the flux is confined within a magnetic core, but a small fraction of the flux escapes from the core into the surrounding low permeability air. This flux out the core is called the leakage flux. So, we sometimes ignore it, or we can use it as per required if we need a very accurate results, but for the time being we can ignore it. Instead of having the exact area of integration or the closed surface integral, we just have seen previously that we are using the mean path length. So mean path length obviously will give us the approximated approximation, and means will make it easier not to find the closed surface integral. So the calculation of a reluctance assumes a certain mean path length and cross-sectional area of the core. These assumptions are not really very good, especially at corners. Obviously, we know that at corners, mean path length will not be the same as desired. So mean path length will not be same as desired. So obviously we have to ignore it because we are making an assumptions. Permeability. So in ferromagnetic materials, the permeability varies with the amount of flux already in the material. That we know that they can have the already flux, that is means the stored flux in the ferromagnetic materials. It adds yet another source of error into a magnetic circuit analysis, since the reluctances used in magnetic circuit calculations depend on the permeability of the material. So we assume that in the beginning there is no flux stored in the uh, ferromagnetic material, so that we are not messed up with those calculations. But those calculations are will be required when we are looking at the transient analysis, means just whenever we have in the beginning what happens to the circuit. So that's where they are important. But if we are working on the steady state portion of the circuits or the any machine, so we are not actually bothered about these residual flux which is already stored in the magnetic materials, because that already stored magnetic flux in the material will subside after a few cycles when we will give the uh, when we will apply the source of the current to the magnetic material. So air gap, here we can see that when we ever have the air gap, so the magnetic flux lines always try to follow the straight lines in to from moving from one pole to another pole. But what happens at the edges, what we have called as the fringing effect. So sometimes if we just look at this fringing effect, so how we can handle it somehow, uh, if we say that this is the actual cross sectional area, this is the actual cross sectional area of this ferromagnetic material. But what happens due to this fringing effect, we have this certain extra amount of uh, uh, this cross sectional area that comes. So we can sometimes add, it could be even 5% or sometimes 10% of the actual cross sectional area. So we can sometimes use this as the additional part of this cross sectional area for this air gap path. Now let's look at an example. So here we have given this magnetic circuit, which is a core, and different dimensions are given. And if we look carefully, three sides, this side, this side, and this side, uh, they are of the same uniform width, while this side has different width, which is 10 centimeter, and the width of this is 15 centimeter. Width of this side is 15 centimeter, width of this side is 15 centimeter. And we have a coil which has 200 turns around the one side of the core, and we have given the relative permeability mu r is 2500, and we have to calculate the how much flux is produced in this magnetic circuit. So if we look closely to this magnetic circuit, we can divide this magnetic circuit into two reluctances which have the same width, uniform width. So this side means this side, and this side. We can take them as the one, say we call it as the say R1, and this side we will call it as the R2. This side, this portion, we will call this path as the beautiful R2. So the first thing we need to calculate is their mean path length, which is LC. So for R1 we call it say L1. So because we are taking the mean path length, so we will start from this point. So from this point to this portion, if we obviously mm, that would be half of this 10 centimeter, so it will be 5 centimeter. This path will be 30 centimeter, and again this path will be half of this 15 centimeter, which is 7.5 centimeter, and again from here uh, to this portion, which is 15 centimeter, so this is again 7.5 centimeter, and this length is given as 30 centimeter, so this will be 30 centimeter. Again this mean path length will be 7.5 centimeter, this will be 7.5 centimeter, and this will be again 30 centimeter, and up till this point we will have again this 10 centimeter, so half of this will be 5 centimeter. So I think so in example this is given as L2, and L1 is the path of this length, which is we can see that half of this 15 centimeter, which is 7.5 centimeter, this 30 centimeter, and again this 7.5 centimeter. So here we have calculated all these parameters. So L1, here we have, if you again look at here, थोड़ा सा मैं उर्दू में बता देता हूँ. यहाँ पे जो L1 है हमने इस पाथ को लिया है, ठीक, ये गिवन भी है, यहाँ पे लिखा हुआ है L1, और इसकी जो लेंथ है वो कितनी होगी, इसकी जो विड्थ है इसका हाफ, क्योंकि मीन लेना है हमने, मीन पाथ लेंथ ले रहे हैं ना, तो ये हमारे पास इसका ये 15 सेंटीमीटर, इसका तो हाफ कितना हो जाएगा 7.5 सेंटीमीटर, और सिमिलरली ये तो पूरी आ जाएगी 30 सेंटीमीटर, और अगेन ये क्योंकि इसकी जो विड्थ है वो 15 सेंटीमीटर है, तो हाफ इसका कितना हो जाएगा 7.5 सेंटीमीटर. सो L1 क्या आ जाएगा 7.5 सेंटीमीटर प्लस 30 सेंटीमीटर प्लस 7.5 सेंटीमीटर. सो हमारे पास ये कितना आ जाएगा 45 सेंटीमीटर. अब इसकी जो डेप्थ गिवन है हमारे पास वो है 10 सेंटीमीटर. सो क्रॉस सेक्शनल एरिया कितना बन जाएगा इसका 10 into 10 100 centimeter square. So the reluctance can be calculated then from this basic relation that we know, mu L1 by A1. So mu naught mu r L1 by A1, mu naught we know that 4.2 10 to the power minus 7, and mu r is given as 2500 as given in the question. L1 we have calculated it here as 100 centimeter, 45 centimeter, and area is calculated as 100 centimeters. So its units will be ampere turns per Weber. Similarly, this will be L2, this whole path. So we have seen that this portion is 5 centimeter. This portion is 5 centimeter. This portion is 30 centimeter. Again, this is half of the 15 centimeter is 7.5. Again, why I am taking these half lengths? Because we are using the mean path length. So So that's why we will take this half of this 15 centimeter. Similarly, this is again 15 centimeter, so half of this will be 7.5 centimeter, and this is straight path which is 30 centimeter, and here again it, because width is 15 centimeter, so we'll take half of this up till here 15 centimeter, 7.5 centimeter. Again we will take half of this, which is because width is 15 centimeter, so half will be 7.5 centimeter, and this L2 is again 30 centimeter, and this width is 10 centimeter, so we will take half of it is 5 centimeter. So by adding all these lengths, we will get it to the mean path length of this second path. The second reluctance is 130 centimeter. So area here will be, because its width is 15 centimeter and depth is 10 centimeter, so it will be 15 into 10 centimeter square, which is 150 centimeter square. So similarly R2 can be calculated here. So we can write down like this here as R1 and R2 the flux that we need to calculate this flux, and this is the magnetomotive force. N is given as I think so 200 tons, and so here now we can calculate this equivalent circuit that we have calculated here. uh, Equivalent circuit that we have, this is R2. So we are calculating this flux. So R equivalent, because they are in series. How we know that they are in series? If we look at this core, so because the flux that is flowing in this so obviously the direction of the flux can be calculated, that modified right hand rule. So obviously that will be, if we curl our fingers around the around this coil, so we will find out that the flux is moving going upward, and the magnetomotive force will be positive and negative like this. So the flux is flowing, and that flux has only a single path, so it means that the reluctances are in series. So here it is R1 and R2. So we have calculated R1 and R2, and their sum is 41,900 ampere turns per Weber. And the total magnetomotive force I is 1 ampere. So magnetomotive force will be simply Ni, which is 200 ampere turns. So again, simply by using this relation phi is equal to beautiful F by a beautiful R, which comes out to be 0.0048 Webers. I hope you have understood all these concepts so far we have studied. So I will suggest you to solve this example by your hand, and also solve some of the problems from the exercise given at the end of this chapter. If you have any queries, you are free to ask me. You can ask me directly to my email address, or um, just leave a comment here. I will inshallah answer your queries. Assalamu alaikum wa rahmatullahi wa barakatuhu.